let's go ahead and pop out the chat here for us. Sorry, it's taken me a moment. Been a little bit since I have streamed for everyone and done a class, but can everyone hear me okay? Let's see. Yeah, let me know if you guys can hear me at all. Hopefully you can. Looks like it should be picking it up. And we'll wait a few more minutes. Awesome. Sweet. Well, now that everyone can hear me, and I believe it is 2 o'clock, let's go ahead and get started. So I'm just going to go ahead and smack this on top of my course. So all of the notebooks that we're going to be using are still out of the Practical Deep Learning for Coders. It is over in this fastinference. Disregard this text, I got to get rid of it. But we're going to be looking at this intro and ONNX. And I also need to get rid of those pre-trained models, apparently. But let's go over fastinference, kind of where it came from, what the idea was, and what was sort of my thought process behind doing it. So fastinference sort of came about when I was trying to take our fastai code and push it to basically to inference. And we were doing a project where it required us to have as fast of inference as possible, so as close to real time as we possibly could get. And what I was sort of noticing was the raw fastai format was a little bit slow, and I'll sort of go into why a little later. And so for the last few weeks, I've sort of been figuring out where we can plug and play various ideas and sort of create a fastai PyTorch hybrid of sorts. And so today we're going to look at what that looks like from a torch perspective, from a fastai and PyTorch perspective, along with from an ONNX perspective. This is going to be a little mini series, so for those of you that have enjoyed my teaching style, we're going to go all through fastinference as it's being developed, because it's still being developed currently, with sort of what's been ironed out. So along with fastinference, we have a few different modules for examining your results. So for instance, those of you that joined me for the tabular sessions, I'm sure you remember the permutation importance. So that's going to be chucked in there along with dependency plots made by a wonderful gentleman on the forums by the name of Pack. He's been doing a lot of work with that, so stay tuned to learn more about that in the next few weeks. But in the meantime, let's sort of just jump in. So fastinference can be pip installed. I tried to adjust some bugs earlier, so it might not be in the latest version. But all of this will work on the latest pip version. So we're going to go through and just make a normal tabular data bunch along with some tabular learners. So just simply fastai2, path, data frame, the usual stuff to set up the adult sample data set. We'll make our tabular pandas and build our data loaders. Now specifically the two functions that we're going to be wanting to look at is predict and getPreds. because as we know, predict works on one row and get preds works on any number of rows. So we want to sort of dictate and see how the speed up changes. Depending on the scope, so whether it's vision or tabular or maybe text, each one has its own different variability. But when someone tried this out on text last night, he said he got a 6 times speed boost. So keep that in mind, and we'll try and teach you sort of how it all works. So for our test, everything will be run on CUDA. Nothing is going to be run on CPU specifically. And so as you can see, predict takes about 280 milliseconds, while get preds takes about 22 milliseconds. And as we all know, predict is a little bit slower of a function for a few reasons. It has to decode all of our outputs. It has to build the data loader itself. So there's a bunch of mini bits that involve this 280 milliseconds that we're going to look into. Now, with those 280 milliseconds and 21 milliseconds, let's focus on the 21 milliseconds. Because in reality, this should be pretty close to a PyTorch, basically running it in raw PyTorch. So we'll go ahead and time that. So this is what your PyTorch inference loop looks like, for those of you that have never seen this before. This is how you can take fastai, import it directly to PyTorch, and get rid of all of the fastai bits except for the data loaders, which is also what this fastinference library is designed to be. So all we do is grab the first batch from that test data loader, and then to run it, it's set the model to eval, and then pass it to our learn.model, because our model is just PyTorch. We can see half a millisecond. That's a very, very large gap from 280 milliseconds, and it's still a gap from the 22 milliseconds. So why? Well, first let's look at what our raw PyTorch model inference outputs. So we can see we have these raw probabilities, and they definitely do not look like what we were expecting. You know, for those of you that have run predict and sort of looked at what the model's output is, we should be seeing something where like this says 0.9 and this says 0.1 or something like that, not this negative almost 0 and 0.2. Now the reason for that is in our loss function exists two properties, activation and decodes, and both are run at two very different times. So activation in our case applies a softmax. So what that means is the softmax value sums all of these up to 1. So we have 0.4925 here and 0.5075 here. This is what we're expecting. And so you can disable this or enable this in what we're going to be making essentially, because that can be useful for a few cases. If you're doing multi-label, right, where you're trying to say, tell my model I don't know, but we want to apply a threshold on those raw outputs, that comes right here. This is where you'd apply that threshold. And so you'd want a way to deal with the raw probabilities. Now, if we then look at the decodes of our loss function, and you can apply the activation here, you don't have to, because softmax is still going to have the same thing as here, just as more readable for us. We can see we get a value of 1, so it's class 1. But again, we can skip that activation and just put it in. All right, so this is how we take raw model output and decode it to a class number or to our raw probabilities. And this is what predict gives us. We have that class ID, that 1, the raw or the softmaxed probabilities, and our input that was sent in, our decoded input, along with the predicted output, I believe. So if we time this predict pipeline, we're still around half a millisecond. So why does this take 280 milliseconds when we just did the same thing at half a millisecond? And what I can say is I stripped out the callback system essentially. And the reason for that to me is we don't need callbacks in inference in most cases. Some cases you absolutely do, but in most cases you don't. And so that's where this can be applied. And for those of you that do need your callbacks in the inference pipeline, you pretty much know what those callbacks do anyways. So you can very easily just plug it in rawly here into what our training loop is going to wind up looking like. So now let's run with fast inference. So for the specific inference speedups and the inference pipelines, we want to call from fast inference import inference. And let's see how long it takes for us to do a predict and a test data loader now. Yes, so what is the difference between get preds and predict? When do you use which? It is surprising why predict is taking so long. Wonderful question, Gloria. So predict will go through and decode basically everything. It also has to build the data loader, which let me see if I included it in here. I did not, but even building the data loader itself, like this line right here, takes around 180 milliseconds. Now, we don't see that here. We just see the 21. Well, that's because predict has to build that test data loader. And so 180 of those milliseconds is coming from this. It's coming from this particular line. That's part of it. The other part is kind of the callback system and sort of how FastAI abstractly does everything, which I just want to say on record, works great during training. That is what it was designed to be for. And for everyone else where necessarily inference time doesn't matter, then absolutely go ahead and use it. They were smart about how they went about it. And the biggest flaw with this is you lose the callback system. And so it's not that it's flawed. It is perfect at what it does. Just for us, we might not need callbacks in the inference. So that is why predict also takes so long. Predict does a bit more than just get preds does. Like if I go through and try and see, I might have to restart everything. Let me see what this says. Nope, I don't. So if we do learner.predict here, we're just going to go through and look at the source code. So where all that comes into play is get preds and how their get preds works, which I know I go over in a moment, so we'll get to that a little later. And I'll kind of explain what I mean by that. And honestly, it could be the very next thing. Now, there we go. So this is what I was talking about right here. For one input, it takes 15 milliseconds just to build the input. So what we should see is about 25 minus 15 is the time that it takes for get preds. And that's almost exactly what we see here. So this is with the new fast inference version. So we know for a fact that at the very least 15 of those milliseconds that come from predict comes from building the test data loader. Now let's go look at the two different methods. The first one we're going to look at is FastAI's get preds. It's a mess. I'm not going to, in terms of readability, if you just want to get down to the nitty gritty, but I'll walk us through sort of what all's going on here, and then we'll look at my version. So the first thing we do is we build a new data loader if data loader is not given. So all this does is says, say the ID is 1, then we'll run get preds on our validation, which disables the shuffling and the drop last. Now then, if we have to reorder everything, this is especially the case if we have like text. You'll need to reorder. We've got some time in the sense we have to reorder everything. Then we have to have a gather preds callback, context managers, keep track of the context managers, and then run through FastAI's way of grabbing everything. Now, FastAI's way of grabbing everything means run through all the steps in the callback system and in the context manager. And so that's why this looks a little weird. In order to fully kind of understand everything, you should go look at the source code, but this is fairly simple to read if we just look at what it's doing. Okay, so we're going to call the everything that happens before epoch, everything whenever we validate, everything we do after the epoch, activate our loss function's activation, grab all the tensors from it, and then work towards getting something that's readable for the user. Now this is a lot to take in, and you kind of have to go through various rabbit holes to kind of get everything. We're going to try and recreate it from a fast inference perspective with one other benefit. Instead of returning the index, we're going to give you the option to return the raw classes as well, with obviously our input, because this is something that I know a lot of people, including me, would like. So this is our version of getPreds. So we notice that we have a few different options here. We have raw outs, decoded loss, and fully decoded. So let's go over kind of what's going on here, and then we can get over to the raw outs, decoded loss, and fully decoded. For those of you with a keen eye, you'll know that this is just a PyTorch loop whenever it takes into account our model. So a few things we have to keep track of is, do we have multiple inputs? This doesn't handle multiple outputs yet. If it becomes a feature request, and if you want that, go ahead and put it in GitHub. Open an issue and open a request for that. In the meantime, though, I'm mostly focused on getting ONNX support and the tabular stuff working. So it's not high in my priorities, but if people would like that, then we'll go ahead and do that. Otherwise, we make sure that we know that we have multiple inputs, and we give ourselves an array for each of our inputs. Then we set the model to evaluation mode, which you have to do for all PyTorch models. And then we just simply say for batch and data loader, without keeping the gradients, if we have multiple inputs, then in my input array, append the batch at that input. So that way we keep track of our inputs separately, which can help us with restructuring everything. Otherwise, just input our batch at our number of inputs, which basically should be 1. So this is another way of saying 1. And then now that we have our inputs, let's look at how we get the outputs from our model. So we see here, if decoded loss or fully decoded, so that is, I want my fully decoded input and output, and that loss function decoding, then I grab my output, I append that raw output to my raw values, and then I attach to the decoded output the loss function's decodes. So basically what that does is it says if you want a decoded loss or a decoded output, then we're going to go ahead and just keep track of the loss function's decoded value. Otherwise, we'll just put in the raw value. We'll concatenate all of them and turn it to the CPU and to a numpy array. Because if we have raw, no matter what, we're going to keep track of the raw. Then from there, if we decode or have decoded loss, we're going to concatenate all of those together. That way we can pass them all at once. And then if we don't want our raw output, so if it's false, we're going to try and see if we can pass the activation of our loss function to those raw values. And if that doesn't necessarily work, because not all loss functions will have activations, sometimes they might just have a decode, then we'll just pass the decoded out. Otherwise, just pass in the raw. So basically, it's a few different ways for us to grab any step in the decoded process we possibly could want. Because then at the end, if you want fully decoded, I have a private method for us to fully decode our input and output. And if we have a decoded loss, I have a special function for decoding the loss function. And if we set everything to false, from false to true, so that's raw outputs are true, decoded loss is false, it's only 7.5 milliseconds. Now that is not, our less than a tenth. So if you want the raw outputs and just return to your user the raw output from your model, just have this. Just have this as your evaluation. Otherwise, all the benefits that don't come from that half millisecond is all of this decoding, which I have done very rigorous testing to make sure it is sped up as fast as we possibly can. So now we basically managed to bring it down a little bit further because we're at 7.5 with everything false compared to 8.8. So you can save about a millisecond or so. Now, predict and get preds will actually return the same thing, which is a little bit different compared to just FastAI's predict versus get preds. So what I mean is if I pass with input to predict, you can see that we'll get a name, a prediction, and the input. So here I'll pass the first row, say with input, we get our name, the activated probabilities. This is always set to the activation probabilities, just so you're aware. And then we have the input. And if we have get preds, you'll notice that we have the predictions in their class name and their probabilities. And get preds also has this, remember the raw outs that we mentioned, the decoded loss, and the fully decoded. So if we look at those raw outs and we pass it to true, we would expect them to not have that softmax applied first, which they do not. If I pass decoded loss to false, we don't get a name, so we just get the raw probabilities. And then if we want the name, probabilities, and the input, we just pass fully decoded. First three rows, and our first three rows. And this works with every single application inside the fastai library. I believe except language models. I don't think it works as efficiently for them yet. I have to see. Or you guys can try and find out, but I think it will. I've personally just tested this on classification. So I sort of went over a lot there. Are there any questions? Is there anything you want me to explain a little bit further? The idea behind this library is you don't leave regular fastai in the sense of what everything's called. So that's why I have it as predict and get pred. So that way everything is still the same for you guys. And nothing gets weirded out by special functions that are added to learner and whatnot. It's the exact same format, just with a little bit of a speed boost. In the meantime, while I wait for you guys to get back with me on that, if not, then we'll go ahead and do ONNX. Thank you, Gloria. So it might not take the full hour to do this just with what I have planned since we're already to ONNX, and this is honestly super quick. So fast inference doesn't work with regression, right? It is untested with regression. I believe it should. If not, I'll have that working within the next few days. And honestly, with my workload, it probably will be the next day. But I will test it and get back with you on if it works or not. Otherwise, yeah, so I will test it tonight with regression and inference with text models, not text classification models, but text models themselves, language models. And I will get back with you guys on if that works or not. Otherwise, we'll get started on the ONNX support. Now, ONNX is something that a lot of people want because it's essentially a way for you to speed up your PyTorch code, and it's also in C++, and so it works everywhere. And I decided that I wanted to try and import it because the other thing I learned about is ONNX recently came out with a CUDA support. And so when you install fastinference, it installs something called ONNX Runtime GPU. And so that is their GPU support. And I'm going to show you guys sort of the steps to integrating it in the fastai framework. It involves a new export function and a new class function. That's all it is, and everything else works exactly the same way. So I'm just going to quickly, make a learn, and then we'll go ahead and call, at the end of it, learn to ONNX. Now this will do two different things. Normally when you do learn.export, fastai will basically pickle the entire thing, which isn't what we want. I just go pickle the data loader specifically, because that's really all we need. So if we go through and I sort of show you what that looks like, because I do like to be, I like to show you guys what's going on. So if we see here, this is the entire to_ONNX function. And we keep track of the batch size and set it to 1 when we export. This is sort of Torch's ONNX export, which takes a raw output. But the bit that I want you guys to notice, fastai, is we call this data loaders new empty. Also, since the loss function is tied to the learner, I want to add that to my data loader. And then I just torch save it away as a pickle file. And that's all that's needed. So anytime you want to just save your data loaders, and you might not necessarily have a data loaders.save method like I believe the text data loaders do, this line right here is actually all you need for that to work. Let's go back to ONNX. So now we have a .ONNX function and we have a .pickle file. So to load both of those back in one line of code, you call fastonix and pass in your file name without the extension. And this will be like a path, same thing you do with like learn.export, learn load, whatnot. Now, what you can do here is predict, get preds, and make a test data loader, which for inference, that's about all you need. So let's see how long our ONNX learner takes to do get preds. 3.4 milliseconds, which not only beats our get preds, but also beats our predict of 25 milliseconds. And the best part is it's the exact same output. We have our name and our probabilities. So all that changed was what we load our model from. Now, it doesn't currently support returning the raw input. This is something I need to work on. But for most of you guys doing this sort of work, I don't believe you need the raw input. In some cases you do, like segmentation. I know it's nice to have the raw output that way, raw input that way you can say put it over the mask. But for the most part, this is what it supports right now. And then I'll just work on that a little later. And the ONNX get preds method looks very similar to what we made before. The reason why I couldn't just say use the actual get preds is because ONNX works in NumPy, so I have to work around that a little bit. And the other thing is predict doesn't necessarily work the same as you would expect. So for most any problem, you should use get preds, even if it's a single one like we did right here. The reason for that is predict is straight up for one item. So you can pass in some tensors, or you basically don't use it unless you have your NumPy arrays. So now predict is sort of a helper function. But that's sort of what I've done to speed up fastai2 with fastinference. And again, I want to reiterate one more time, fastinference is a training module. It is not necessarily an optimized inference module, and this is why. So that's sort of where this came from, and I'm still training my models in regular fastai no matter what, because I'm not 100% sure that this will support training on all modules, especially because you just get rid of the the context managers, which you don't really want to do during training. So train in fastai, bring to fast inference, and then take to ONNX or just do regular inference is what my framework will be for the foreseeable future. Now, I do have a documentation website for this. So if we go to Mueller's ER, GitHub IO, fast inference, I'm working on expanding it a bit more. You can see what all I currently support. There is some works for tabular, but you can see we have the ONNX documentation. It might not be too verbose. I'm gonna put everything I have here in the tutorials. It's like we have tabular interpretation here, general inference, which basically goes over what I just did. So here we have a vision example, and then we have a tabular example. I don't have a text example yet, but they all work the same way. So, are there any questions to that, really? That was all I had planned on talking about today. I know that wasn't too long. It was about 30 minutes. The next one we're going to cover will be porting over, FastShap, because FastShap now lives in here. Along with there's a few other sort of tabular methodologies for interpretation that are in the works this weekend that I'm going to be working on. But besides that, are there any questions? Any plans for dropout? Personally, no. Not me specifically, because I'm not that familiar with dropout. If one of you is familiar with it and wants to try and incorporate it into this training loop, that I mentioned here, or not training loops, to the get predictions method here, if you say have dropout enabled, do X, Y, Z, you absolutely could. The best way I would possibly do it is, since dropout's applied, I don't quite remember if dropout's applied on the activation or on the decodes, but whichever one it's applied to, how I would go about doing it is when we run get preds, you would, where we have our start decoding the loss function, that's where you would apply your dropout. So that'd be how you do it. If any of you guys manage to get it working, please put in a PR. I don't have the time to do everything as much as I would love to. So if you guys want that support, please help me out. Otherwise, I think that is about it for me. All of this is living inside the Practical Deep Learning for Coders. So I'm going to put, when I'm doing the next one as well, inside that thread. And we'll just sort of tag it along with the lecture. Otherwise, thank you guys for joining me today. I have missed, being in this sort of teaching atmosphere personally. Um, I'm also going to make no promises to the tech stuff. We'll get there when we get there. But in the meantime, I'm going to be running this little mini series for you guys, sort of walking me through this. So thanks for joining. I will see you guys next time. Thank you.